Hello everyone, this is Lab 7. It's a big one talking about controller design and compensator design. They're interchangeable, controllers and compensators. Okay, so let's get into it. Let's say we have the system here, some feedback system, and the error is going to go into this guy here, and it's going to output our response. And we want the response to behave a certain way. Like we want maybe some percent overshoot, some settling time, stuff like that. Um, but it turns out that maybe that's not some responses, like some overshoot, some settling times are not possible with just this guy right here. We need to add something to it in order to get the responses that we want. So just a quick refresher. The error of the system is where you want to go minus where you're currently at. And where you're currently at is your response, C of S. Where you want to go is R of S. Okay, let's talk about PD controllers. So if we were to put something in here before G of S, this is G of S right here. If we were to put something before G of S such that we get a response that we want, we could use a PD controller. And what it stands for is proportional and derivative. And it looks like this. So basically the error comes in and it gets multiplied by our proportional gain, right? There's nothing else that goes on. It's just it comes in and it's going to be multiplied by some constant and it's going to get something that's proportional to the error. What's also going to happen is we're going to take the derivative of the error, so d error dt, yeah, essentially, and multiply it by our derivative gain. And so if we expand it out algebraically, we get this, right? So our controller is going to be kp plus the derivative of our input times kd. And what the controller does is it says how much more effort do I need to do and in what direction. So real world mechanical PD controller is like a mass spring damper system. So if we have this mass and it's on a frictionless surface, let's say that we want the mass to be at the equilibrium point of the spring. Well, then the system will just take care of itself. So if we have the mass starting, the springs may be compressed or something, and then it's going to, come out, and if it's critically damped, we're going to get a very quick response like this. So it's going to come out like this, and it's going to reach the equilibrium value of the spring. What we see is that each of these terms works to get this critically damped response, and each of these terms are very important. So without Kp, the system's not going to do anything, right? Because Kd is proportional to the derivative of the error, not the error itself. If the error is not moving, right, if it's just a flat line, then that's 0, and Kd is going to be multiplied by 0, and this part that's going into the summation is going to be 0, right? So if we don't have Kp, then we have no reason to move the spring anywhere, or the mass anywhere, and that makes sense. If you just have a dash pot connected to a mass, it's not going to do anything. On the other hand, if we just have a spring, yeah, it's going to want to, go towards the equilibrium point, but it's going to oscillate. And in a perfect world, it's going to oscillate forever. We don't want that either. We want a critically damped system. We want it to get there and stop as fast as possible. So they work together. Kp says we need to move the mass over to the equilibrium point. And the Kd says, okay, slow down. We're reaching the equilibrium point. We need to, hit the brakes, or otherwise we're going to overshoot and do some bad stuff that we don't want. So that's what Kd is, kind of conceptually, or sorry, PD. If we add what's called an I, or an integral part, think of it as a PD but with an I part. And that's how you design these things. Is first you do the PD part, and then you add the I. So let's say that we have the same kind of mass damper system, but now it's going downwards, and we still want to get to the equilibrium point of the spring, or when the spring is not, applying any force. But that's not going to happen just by itself because of the force of gravity. We're going to get some static point of equilibrium, if you remember from vibrations. That's not going to be the same thing as the equilibrium point of the spring. So the spring's going to be applying some force. We don't want that. So what the integral gain will do is it will integrate away steady state error. So if it stops at this equilibrium point, what the integral gain will do is give you that little bit of force needed to get you to the desired point. And mathematically what it is E times dt. And so the integral gain term is proportional to the error times however long you're going for. So let's say our response looks like this. So usually the I term doesn't really interact until later on. So it starts to look like just like a PD response. So it's gonna kind of approach it and kind of level off. Let's say it's damped enough so we're not going to oscillate, right? But we still have the steady state error. Well, the K term's not going to do anything, right? It's already doing its best, but it's stuck, right? Because this is going down. It's like, okay, well, I'm never going to get zero steady state error with just a spring if my mass is face downwards. What the integral gain does is it says, well, there's still some error here, right? That's the difference here. There's still some error, and we're continuing on with time. And so this dt term is going to grow with time, and the error here is constant. So we're going to get sort of this linear increase in our integral term. And that is going to, say the integral term is this fan here, and it's the fan speed. Well, the fan speed is going to keep increasing and increasing and increasing until finally we can push this mass up to the desired point. So that's what it does. It removes steady state error from the system. That is its main job. So let's do an example. Let's start with a PD controller. Here we have the system. This is what we're looking at here. And again, a PD controller is going to be some proportional thing, some proportional gain, and then a derivative gain times, taking the derivative of the error. Remember, 1 over s is an integral, so if you have a signal like an error coming in and you multiply by 1 over s, you're integrating it. If you multiply it by just s, you're taking the derivative. So if your error is displacement, it's going to turn it into a velocity. And so that's why this looks like a dash pot. It's because dash pots respond to velocity and not displacement. So here we are. We're going to multiply c of s, which is in this form, by our g of s, and we obtain this here. And we have to figure out what kp and kd are. And that's not clear because we don't know what we want the system to do. So if we read further on here, we see, okay, we want a 16% overshoot, and we want, I think, 1/3 reduced settling time. Okay, well, continuing on with the math first before I get into the MATLAB. We can factor out, we have this k left over from g, okay, that's fine. We have this guy here. We want to factor out a kd so that we get this form here. And what this is very clearly you can see a 0. It's going to be negative kp over kd. And that's going to be important later. And then we have these 3 poles that are already figured out for us, right? That comes from g. Okay, so now all we have to do is figure out where the 0 is, so that way we get 16% overshoot and a reduced settling time of 1/3. Okay, so let's get into the MATLAB. Looks like I already had some stuff open, so I'll just restart this. So firstly, I'm going to enter in my g, and I'm going to do it in a new format called ZPK, and this is just like the TF function, but this is better if you have factored things because that's just what you input. You input the zeros, the poles, and any loop gains. And so if we did a transfer function, it'd still work, of course, but you need to FOIL this out. I don't want to do that. I'm just going to input the zeros and poles. So we have no zeros, We don't have a zero of value 0. We actually have no zeros because there's no s in the numerator. In the denominator, we have our poles, 0, -4, -6, quite clearly, and then we have 1 loop gain, that's k. Great, so let's run this. Oops. And this is our CISO tool. CISO, I don't know how to say it. And what it is it's a way to design compensators and controllers. And so first we need to specify what our system looks like. It looks like this, right? So if we go here, click this, we can assume a certain form. This will work fine for us. You might say, well, there's too many parts to it. Well, we can just say f is 1 and h is 1, right? We're designing C, right? We're designing C, and G is given to us. So I already did G. I'm going to take it from the workspace, okay? And there's kind of two ways to design compensators and controllers. This is the Bode plot way. This is the root locus way. We're going to do the root locus way. So I'm going to maximize that. Great. So with this, we can see the root locus, and you should know what the root locus is by now. It's a plot of, this guy here with k ranging, right? So you might think maybe a couple weeks ago, well, how does k influence the poles of the system? It's in the numerator. Well, when you do the feedback function, right, k goes on the denominator just because how that math works out, right? We did that last week. So k does actually impact the pole placement of, this whole transfer function. Okay, so here's the root locus, and we can actually add design requirements. So you should know that like overshoot, if you say I want my overshoot to be 16%, it's going to look like a line coming out of the origin. So for example, if I say, sorry, I meant overshoot. If our overshoot is 16%, it's going to look like a line coming out of the origin, right? So what this is saying is that here are the possible pole placements for our system, right? That's this blue line. But if we want exactly 16% overshoot, it's got to be at this intersection. That's what it's saying. So that's fine. Looks like it's possible to get 16% overshoot with our current system. That's great. But we also have a different requirement. We have to get a settling time reduction of 1/3. So that's why we need the C controller, right? We wouldn't need a C controller for just this. We just need a certain value of K, and that would work just fine. But we need to reduce the settling time. So how we do that is we add another requirement, settling time, and we're going to move it to what it is currently at. So if we are at 16% overshoot, we have a settling time of about 3.25, not just 5, 3.25. And so we want 1/3 of that, right? So if we have our current system, it looks like this, right? If we have a k value such that we have 16% overshoot, our settling time is going to be 3.25 seconds. We want to reduce that by 3. So 3.25 divided by 3 is 1.08. And so what I'm going to do is I'm going to move this line to 1.08 so that it has 1.08 seconds. Okay, now we have a problem because we can't get 16% overshoot and a settling time of 1.08 at the same time. It just doesn't work out. What we need to do is move the root locus such that it intersects these points here and here. And we can do that by adding a 0. So if we look back to what a PD controller is, it's a 0, right? Right here. What we're doing is adding a 0 at minus kp over kd. Okay? So how we do that is we go to the root locus editor. We're going to add a 0. And we're going to place it. And wow, it changes the root locus a lot. So we're going to move this around until we get, I'm going to zoom in here. Oh, it did it for me. That's nice. See this blue line? We want it to intersect right there. So here's our 0, and looks like we're about there. Great, so now our root locus intersects that point. That is cool. So what does our C look like? We've moved the 0 to looks like about -3, and that's demonstrated here. And if we want a loop gain such that we end up at this point, we can change that value here. So let's go to 10. No, we need more than that. 50, more than that. 70, much more than that. How about just 130? We're getting there. 150. I'm going to say 140. That's pretty spot on. Okay, so that means we've added a 0 or a PD controller, and we have a loop gain of 140, and that does the trick. So what does that look like? So KP over KD is 3, right? That's what this is saying. I have it in a different format here. I have the number that's, I have S being multiplied by 1. This is the same thing. KP over KD is equal to 3, or -3. No, just 3. And then our loop gain is going to be K times KD. So before we added our controller, our loop gain was just K, but since we factored out a KD, that's what we have being, that's also part of the loop gain. So K times KD is equal to 140. So KP over KD is equal to 3, and we found our gain parameter. And that is how you do that.